Another technique that we can use to produce a new matrix is to consider a product manifold and to try to define a metric on this new space. How this is done? Suppose that MIGI with I equal to 1 and 2 are Riemannian manifolds. Then we can define a natural Riemannian metric on M1 times M2. This is known as a product metric, and it is denoted by G1 plus G2, and it is defined by the following formula: G at the point P1, P2 at V1, V2, W1, W2. This pair represent a tangent vector to M1 cross times M2, and the same is true for this pair, and this is equal to G1 at P1 of V1 W1 plus G2 at P2 of W1 W2, where V1 V2 W1 W2 belongs to TP1 M1 plus TP2 M2. This is a space which is identified with TP1 P2 M1 times M2. What is the local expression for G1 plus G2? This is easy to find. In order to do this, suppose that x1, x2, xn and xn plus 1, xn plus m are smooth local coordinates for M1 and M2. Then it is clear that x1, x2, xn, xn plus 1, xn plus m, these are smooth local coordinates for M1 times M2. Now, if you look at this formula, you will see that if you write the metric in this form, you have that Gij is the entry of the matrix denoted this way, and which has the following structure: G1, let's say AB, 0, 0, G2 CD, where G1 AB is the matrix representing the metric G1, and G2 CD represents the matrix giving the local representation of the metric G2. And of course, here you have that AB can vary between 1 and n, and CD vary between n plus 1 and n plus m. The notion of product metric can be generalized. Precisely, the product metric is a special case of the following construction, known as a warped product. In this case, the ingredients are two Riemannian manifolds, correct? I equal 1, 2, and strictly positive function defined on M1 with values in R. Then the warped product denoted by M1 times F M2 is the product manifold M1 times M2 as before, but this time the metric is different. So let's write equip with the metric G1 plus F square G2. This metric is defined by the following formula: G at P1, P2 evaluated at the pairs V1, V2, W1, W2. This is equal to G1 at P, V1, W1 plus F square evaluated at P1 times G2 at P2. I made a typo, sorry, this is P1, and V2, W2, where V1, V2, W1, W2 belongs to TP1M1 plus TP2M2. Clearly, if f is the function which is identically equal to 1, you get the product metric. So the product metric is a special case of a warped product metric. Now let's talk about Riemannian submersion. So suppose that M tilde and M are smooth manifolds pi from M tilde to M is a smooth submersion, and G tilde is a metric on M tilde. We now use the submersion level set theorem. You can find it in the appendix A, which says that every level set of pi this map here that is a subset of the form pi inverse of y with y in M. This is contained in M tilde, of course. Is properly embedded submanifold of M tilde whose codimension that is the difference between dimension of M tilde minus the dimension of pi inverse y equals dimension of M. Let's fix the notation. This manifold will be denoted by M tilde y and at each point x of M tilde we can define the vertical tangent space at x dx equal kernel of d pi x, that is tx of M tilde pi x, and the horizontal tangent space at x hx equal vx orthogonal. It's possible to prove that Tx M tilde can be written as Hx direct sum Vx. And we will use this later. What I want to do now is to give definition of Riemannian submersion. So suppose that M tilde, G tilde, M, G are Riemannian manifolds. And pi is a smooth submersion as before. We say that pi is a Riemannian submersion if for any x in M tilde d pi x is a linear isometry from Hx, which is this space here, onto T pi x M, that is G tilde at x of VW. This must be the same as G at pi of x of d pi x v d pi x of w. In other terms, the pullback of G by pi must coincide with G tilde. It is immediate to prove that this is true. The following examples. 1. Take R n plus k and R and G bar. So G bar denotes the Euclidean metric. This is the Euclidean metric. Let's write n plus k to mark the difference. This is the Euclidean metric on Rn plus k, and this is the Euclidean metric on Rn. And let's take pi to be Rn plus k plus Rn, the projection on the first and coordinates. And it's immediate to see that this map here is a Riemannian submersion. Why? Because G tilde and G are the Euclidean metric, and in this case d pi x v is nothing but then the restriction of a tangent vector to this space to a tangent vector in T, let's say pi x Rn. Another case which is immediate to in which is immediate to see that this is true is the following. Take m times n with the metric g1 plus g2. Sorry, exchange notation. And consider the maps by m from m times n to m by n from m times n to n. These two maps are Riemannian submersion. Why? Because this map here is just the restriction between the tangent space to this manifold here on the tangent space to m or n according to the fact that you are using this map or this other map. Instead, if you use the warped product, it's possible to prove that only this map here is a Riemannian submersion. The reason is the same. Instead, it is not true that pi n is a Riemannian submersion. Why? Because in the formula for the metric for this product, there is an f squared in front of gn, so it is easy to see that this cannot be true. Now let's talk about groups acting on manifolds. I want to provide you definitions that would allow you to understand the following two results. The first one is the following theorem. Suppose that m tilde g tilde is a Riemannian manifold and pi from m tilde to m a smooth surjective smooth submersion suppose that G is a group acting on m tilde. Suppose that the action of G is isometric vertical and transitive on fibers, then this implies that there exists a unique Riemannian metric on M, this manifold here, such that pi is a Riemannian submersion. So what I'm going to do now is to explain the meaning of these words. And later I will present a consequence of this result. I don't prove this theorem because we are behind our schedule, and we will not use this theorem that much. So let's review the maybe the notion of action of a group on a manifold. So suppose that G is a group and M just a set, but we will use these definitions in the case where M is a manifold. So a left action of G on M is a map defined on G times M with values in M, which sends phi p to phi dot p, satisfying the following property: phi 1 dot phi 2 dot p. This is the same as phi 1 composed with phi 2 dot p. Here phi 1 and phi 2 are elements of G. So phi 1 composed with phi 2 is the result of the composition of F1 with F2 using the multiplication, the operation that you have on G. And E dot P equal P for any phi 1, phi 2 in G and P in M. There is a similar definition for the right action of G on M. And when we say that a group G acts on a manifold, then it means that it acts on the left and on the right at the same time. What is the isotropy subgroup? At P in M. P can be chosen arbitrarily, of course. So this is the subgroup GP of G consisting of all elements that fix P. What does it mean? This means that GP is the subgroup containing the elements of G such that phi dot P is P. The action is free. If GP is the identity, the action is effective if phi 1 dot P equal phi 2 dot P for all P in M if and only if phi 1 is equal to phi 2. The action is transitive if for any pq in M there exists phi in G such that phi acting on P gives you Q. Now suppose that M is a smooth manifold an action by a group G on M is said to be an action by diffeomorphisms if for each phi in G the map P goes to phi dot P is a diffeomorphism. If G is a Lie group that is G is also a smooth manifold, so G is has the structure of group and smooth manifold. An action of G on M is smooth if the map phi P phi dot P is smooth. This definition makes sense because G is a smooth manifold and On the left you have the product manifold of G and M, and on the right you have a smooth manifold, so it's clear what is the meaning of smooth map in this case. It's clear that a smooth action is also an action by diffeomorphisms. It is immediate to check that this is true, because what does it mean for an action to be an action by diffeomorphisms? We have to check that this map is a diffeomorphism, so this must be smooth, and this follows from this hypothesis, and we have only to prove that there exists an inverse for this map which is smooth, and the inverse is this, which is also smooth because phi inverse is an element of G, and the action is smooth by hypothesis. I think I gave you all definition about Lie groups, so now I'm ready to tell you when the action is vertical. So remember that we are looking at pairs of manifolds between there exists a map pi. So we have that the action of the group G is vertical if every element phi in G takes each fiber to itself, that is pi of phi dot p coincide with pi at p, for any p in M tilde. The action is transitive on the fibers if for each PQ in M tilde such that pi p is pi q, there exists phi in G such that phi dot p is equal to q. The list of definitions is not finished, unfortunately. It remains to understand when an action is isometric or it's an action by isometries if the map which send x to phi dot x is an isometry. In this case, the metric is said to be invariant under G. So now you have all the definitions which allows you to understand the theorem I presented before. The following corollary, it's more useful for practical purposes. And it says the following. So suppose that you have a Riemannian manifold M tilde G tilde G a Lie group acting smoothly freely properly and isometrically on M tilde, then the orbit space M given by M over G has the unique, as a unique smooth manifold structure, and Riemannian metric. So this says that this object it's a smooth manifold and the Riemannian manifold, such that pi is a Riemannian submersion. I realized that I did not give you the definition of orbit space. I'm sorry for that. I will fix the problem immediately. So if P is a point of M tilde, G dot P defined as the set of points given by the image of P under all the elements of G is what we call orbit of P. The set of all orbits is called orbit space, and it is denoted by M tilde over G. So now it's clear what is this object. Okay, then now let's go back to the tensors, and let's talk about a procedure which allows us to convert vector to covectors and vice versa. We will use this procedure later. So suppose that G is a Riemannian metric on M. Then we can define a map G from Tm to T star M as follows. G hat of V W, this is GP V W for any P in M and VW in EPM. It's possible to prove that this is a bundle homomorphism. I will not provide you with the definition of bundle homomorphism because it's not useful in the sequel and I want to save time. It's clear that what up if we consider smooth vector fields. So this means that x and y are smooth vector fields on M. We have that G at x, y is defined by G, x, y. And this implies two things. One, G hat x, y is linear over C infinity M. And this as a consequence, G at x behaves like a covector. So this is a smooth covector field. And second, the covector field G hat x is linear over C infinity, over C infinity M as a function of x, and this implies that G hat is smooth. For us, the conclusion number one is more useful than the second one. Precisely, let's check how much time I have. Okay. So given a smooth local frame, EI, and its dual coframe, epsilon I, we can suppose that G has the following local representation: Gij epsilon I tensor epsilon j. We can also use the notation epsilon I epsilon j, where this is a symmetric product. We prove that it is the same thing. So if x equal x I EI is a smooth vector field on M, what is the expression of G hat x? The formula I used before says G hat x acting on y, this is just G x y. So we have that G is here. What is Gxy? Gxy is a Gij xi yj if y is equal to yj ej. This implies that G at x is Gij xi, and you have to multiply everything by epsilon j. Why? Because if you let act this object on y, you will get Gij xi yj. The yj comes from this. So this implies that the matrix of G hat coincide with the matrix of G. Now let's introduce the following notation. Xj with the index on the bottom. This is Gij xi. The theta is this element here. This implies that g at x can be written as xj epsilon j. So this means that g at x is obtained by from x by lowering an index, because we started from this formula and we got this one. So we can write this way: g at x equal x flat. This notation here originates from music. This is what we call the first musical isomorphism we will see today. The second musical isomorphism we will see does the converse. So this is what we call, we have to read this as x flat. So we observed before that the matrix of G hat coincides with the matrix of G. We know that this matrix is invertible. So we write this way for the inverse matrix of Gij. We write G with the upper indices, and this means that we can write this formula: Gij Gjk. This is the same as Gkj Gij equal to delta I k. So this means that this is the inverse of this, because if you multiply them this way you get the Kronecker delta function. This says that there exists G at inverse the matrix associated with this map is this. So this means that you can write this way. This is true because G hat sends a vector field onto a covector field. So G hat inverse sends a covector field to a vector field, where omega I is Gij omega j. The notation we use in this case is the following: G at inverse of omega. This is omega sharp, and this is the second musical isomorphism, and the first important example is the following. Suppose that F is smooth, then we can define gradient of F as the vector field given by df sharp. Now, if you look at the construction I presented to you, unfortunately I have to erase something. You will get that gradient of F is Gij EJF times EI. So I used this formula. This is omega I, and I use this formula to get this one. Why? Because omega j is EJF. It's a good point to where to stop. Thank you for your attention.